In statistics, a mixture model is a probabilistic model for representing the presence of subpopulations within an overall population, without requiring that an observed data set should identify the subpopulation to which an individual observation belongs. Formally, a mixture model corresponds to the mixture distribution that represents the probability distribution of observations in the overall population. However, while problems associated with mixture distributions relate to deriving the properties of the overall population from those of the subpopulations, mixture models are used to make statistical inferences about the properties of the subpopulations given only observations on the pooled population, without subpopulation identity information. Some ways of implementing mixture models involve steps that attribute postulated subpopulation identities to individual observations, in which case these can be regarded as types of unsupervised learning or clustering procedures. However, not all inference procedures involve such steps. Mixture models should not be confused with models for compositional data, that is, data whose components are constrained to sum to a constant value. However, compositional models can be thought of as mixture models, where members of the population are sampled at random. Conversely, mixture models can be thought of as compositional models, where the total size of the population has been normalized to 1. Structure of a mixture model. General mixture model A typical finite-dimensional mixture model is a hierarchical model consisting of the following components: n random variables corresponding to observations, each assumed to be distributed according to a mixture of k components, with each component belonging to the same parametric family of distributions but with different parameters, n corresponding random latent variables specifying the identity of the mixture component of each observation, each distributed according to a k-dimensional categorical distribution, a set of k mixture weights, each of which is a probability, all of which sum to 1, a set of k parameters, each specifying the parameter of the corresponding mixture component. In many cases, each parameter is actually a set of parameters. For example, observations distributed according to a mixture of one-dimensional Gaussian distributions will have a mean and variance for each component. Observations distributed according to a mixture of v-dimensional categorical distributions will have a vector of v probabilities, collectively summing to 1. In addition, in a Bayesian setting, the mixture weights and parameters will themselves be random variables, and prior distributions will be placed over the variables. In such a case, the weights are typically viewed as a k-dimensional random vector drawn from a Dirichlet distribution, and the parameters will be distributed according to their respective conjugate priors. Mathematically, a basic parametric mixture model can be described as follows. In a Bayesian setting, all parameters are associated with random variables, as follows. This characterization uses f and h to describe arbitrary distributions over observations and parameters, respectively. Typically h will be the conjugate prior of f. The two most common choices of f are Gaussian, also known as normal, and categorical. Other common possibilities for the distribution of the mixture components are, binomial distribution, for the number of positive occurrences given a fixed number of total occurrences, multinomial distribution, similar to the binomial distribution, but for counts of multi-way occurrences, negative binomial distribution, for binomial-type observations but where the quantity of interest is the number of failures before a given number of successes occurs, Poisson distribution, for the number of occurrences of an event in a given period of time, for an event that is characterized by a fixed rate of occurrence, exponential distribution, for the time before the next event occurs, for an event that is characterized by a fixed rate of occurrence, log normal distribution, for positive real numbers that are assumed to grow exponentially, such as incomes or prices, multivariate normal distribution, for vectors of correlated outcomes that are individually Gaussian distributed, a vector of Bernoulli distributed values, corresponding, for example, to a black and white image, with each value representing a pixel. See the handwriting recognition example below. Specific examples equals. Gaussian mixture model. A typical non-Bayesian Gaussian mixture model looks like this. A Bayesian version of a Gaussian mixture model is as follows. Multivariate Gaussian mixture model. A Bayesian Gaussian mixture model is commonly extended to fit a vector of unknown parameters, or multivariate normal distributions. In a multivariate distribution, one may model a vector of parameters using a Gaussian mixture model prior distribution on the vector of estimates given by, where the if vector component is characterized by normal distributions with weights, means and covariance matrices. To incorporate this prior into a Bayesian estimation, the prior is multiplied with the known distribution of the data conditioned on the parameters to be estimated. With this formulation, the posterior distribution is also a Gaussian mixture model of the form, with new parameters and that are updated using the M algorithm. Although M-based parameter updates are well established, providing the initial estimates for these parameters is currently an area of active research. Note that this formulation yields a closed-form solution to the complete posterior distribution. Estimations of the random variable may be obtained via one of several estimators, such as the mean or maximum of the posterior distribution. Such distributions are useful for assuming patch-wise shapes of images and clusters, for example. In the case of image representation, each Gaussian may be tilted, expanded, and warped according to the covariance matrices. One Gaussian distribution of the set is fit to each patch in the image. Notably, any distribution of points around a cluster may be accurately given enough Gaussian components, but scarcely over k equals 20 components are needed to accurately model a given image distribution or cluster of data. Categorical mixture model. A typical non-Bayesian mixture model with categorical observations looks like this, as above, as above, as above. Dimension of categorical observations, for example, size of word vocabulary, probability for component of observing item, vector of dimension composed of must sum to 1, the random variables. A typical Bayesian mixture model with categorical observations looks like this, as above, as above, as above. Dimension of categorical observations, for example, size of word vocabulary, probability for component of observing item, vector of dimension composed of must sum to 1, shared concentration hyperparameter of for each component, concentration hyperparameter of, the random variables. Examples. A financial model equals. Financial returns often behave differently in normal situations and during crisis times. A mixture model for return data seems reasonable. Sometimes the model used is a jump diffusion model, or as a mixture of two normal distributions. See Financial Economics Challenges and Criticism for further context. House prices equals, assume that we observe the prices of n different houses. Different types of houses in different neighborhoods will have vastly different prices, but the price of a particular type of house in a particular neighborhood will tend to cluster fairly closely around the mean. One possible model of such prices would be to assume that the prices are accurately described by a mixture model with k different components, each distributed as a normal distribution with unknown mean and variance, with each component specifying a particular combination of house-type neighborhood. Fitting this model to observed prices, for example, using the expectation maximization algorithm, would tend to cluster the prices according to house-type neighborhood and reveal the spread of prices in each type neighborhood. Topics in a document equals, assume that a document is composed of n different words from a total vocabulary of size v, where each word corresponds to one of k possible topics. The distribution of such words could be modeled as a mixture of k different v-dimensional categorical distributions. A model of this sort is commonly termed a topic model. Note that expectation maximization applied to such a model will typically fail to produce realistic results, due to the excessive number of parameters. Some sorts of additional assumptions are typically necessary to get good results. Typically two sorts of additional components are added to the model. A prior distribution is placed over the parameters describing the topic distributions, using a Dirichlet distribution with a concentration parameter that is set significantly below 1, so as to encourage sparse distributions. Some sort of additional constraint is placed over the topic identities of words, to take advantage of natural clustering. For example, a Markov chain could be placed on the topic identities, corresponding to the fact that nearby words belong to similar topics. Another possibility is the latent Dirichlet allocation model, which divides up the words into D different documents and assumes that in each document only a small number of topics occur with any frequency. And writing recognition . The following example is based on an example in Christopher M. Bishop, Pattern Recognition and Machine Learning. Imagine that we are given an n black and white image that is known to be a scan of a handwritten digit between 0 and 9, but we don't know which digit is written. We can create a mixture model with different components, where each component is a vector of size of Bernoulli distributions. Such a model can be trained with the expectation maximization algorithm on an unlabeled set of handwritten digits, and will effectively cluster the images according to the digit being written. The same model could then be used to recognize the digit of another image simply by holding the parameters constant, computing the probability of the new image for each possible digit, and returning the digit that generated the highest probability. Direct and indirect applications . The financial example above is one direct application of the mixture model, a situation in which we assume an underlying mechanism so that each observation belongs to one of some number of different sources or categories. This underlying mechanism may or may not, however, be observable. In this form of mixture, each of the sources is described by a component probability density function, and its mixture weight is the probability that an observation comes from this component. In an indirect application of the mixture model, we do not assume such a mechanism. The mixture model is simply used for its mathematical flexibilities. For example, a mixture of two normal distributions with different means may result in a density with two modes, which is not modeled by standard parametric distributions. Another example is given by the possibility of mixture distributions to model fatter tails than the basic Gaussian ones, so as to be a candidate for modeling more extreme events. When combined with dynamical consistency, this approach has been applied to financial derivatives valuation in presence of the volatility smile in the context of local volatility models. This defines our application. Fuzzy image segmentation . In image processing and computer vision, traditional image segmentation models often assign to one pixel only one exclusive pattern. In fuzzy or soft segmentation, any pattern can have certain ownership over any single pixel. If the patterns are Gaussian, fuzzy segmentation naturally results in Gaussian mixtures. Combined with other analytic or geometric tools, such spatially regularized mixture models could lead to more realistic and computationally efficient segmentation methods. Identifiability. Identifiability refers to the existence of a unique characterization for any one of the models in the class being considered. Estimation procedure may not be well defined and asymptotic theory may not hold if a model is not identifiable. Example let J be the class of all binomial distributions with n equals 2. Then a mixture of two members of J would have and P2 equals 1 APO AP1. Clearly, given PO and P1, it is not possible to determine the above mixture model uniquely, as there are three parameters to be determined. Definition consider a mixture of parametric distributions of the same class. Let be the class of all component distributions. Then the convex hull K of J defines the class of all finite mixture of distributions in J. K is said to be identifiable if all its members are unique, that is, given two members P in par euro squared and K, being mixtures of K distributions and car euro squared distributions respectively in J, we have P equals par euro squared if and only if, first of all, K equals car euro squared and secondly we can reorder the summations such that I equals I euro squared and I equals I euro squared for all I. Parameter estimation and system identification. Parametric mixture models are often used when we know the distribution Y and we can sample from X, but we would like to determine the I and II values. Such situations can arise in studies in which we sample from a population that is composed of several distinct subpopulations. It is common to think of probability mixture modeling as a missing data problem. One way to understand this is to assume that the data points under consideration have membership in one of the distributions we are using to model the data. When we start, this membership is unknown, or missing. The job of estimation is to devise appropriate parameters for the model functions we choose, with the connection to the data points being represented as their membership in the individual model distributions. A variety of approaches to the problem of mixture decomposition have been proposed, many of which focus on maximum likelihood methods such as expectation maximization or maximum a posteriori estimation. Generally, these methods consider separately the question of parameter estimation and system identification, that is to say, a distinction is made between the determination of the number and functional form of components within a mixture and the estimation of the corresponding parameter values. Some notable departures are the graphical methods as outlined in Tata and Locke, and more recently minimum message length techniques such as Figueiredo and Jane, and to some extent the moment matching pattern analysis routines suggested by McWilliam and Lowe. Expectation maximization expectation maximization is seemingly the most popular technique used to determine the parameters of a mixture with an a priori given number of components. This is a particular way of implementing maximum likelihood estimation for this problem. M is of particular appeal for finite normal mixtures where closed-form expressions are possible, such as in the following iterative algorithm by Dempster al. with the posterior probabilities. Thus, on the basis of the current estimate for the parameters, the conditional probability for a given observation x, t, being generated from state S is determined for each t equals 1, a nn being the sample size. The parameters are then updated such that the new component weights correspond to the average conditional probability, and each component mean and covariance is the component-specific weighted average of the mean and covariance of the entire sample. Dempster also showed that each successive M iteration will not decrease the likelihood, a property not shared by other gradient-based maximization techniques. Moreover, M naturally embeds within it constraints on the probability vector, and for sufficiently large sample sizes positive definiteness of the covariance iterates. This is a key advantage since explicitly constrained methods incur extra computational costs to check and maintain appropriate values. Theoretically, M is a first-order algorithm and as such converges slowly to a fixed-point solution. Redner and Walker make this point, arguing in favor of superlinear and second-order Newton and quasi-Newton methods and reporting slow convergence in M on the basis of their empirical tests. They do concede that convergence in likelihood was rapid even if convergence in the parameter values themselves was not. The relative merits of M and other algorithms vis-à-vis convergence have been discussed in other literature. Other common objections to the use of M are that it has a propensity to spuriously identify local maxima, as well as displaying sensitivity to initial values. One may address these problems by evaluating M at several initial points in the parameter space, but this is computationally costly, and other approaches, such as the annealing M method of Ardea and Nakano, may be preferable. Figueiredo and Jane note that convergence to meaningless parameter values obtained at the boundary is frequently observed when the number of model components exceeds the optimal true one. On this basis, they suggest a unified approach to estimation and identification in which the initial n is chosen to greatly exceed the expected optimal value. Their optimization routine is constructed via a minimum message length criterion that effectively eliminates a candidate component if there is insufficient information to support it. In this way, it is possible to systematize reductions in n and consider estimation and identification jointly. The expectation maximization algorithm can be used to compute the parameters of a parametric mixture model distribution. It is an iterative algorithm with two steps, an expectation step and a maximization step. Practical examples of M and mixture modeling are included in the SOC demonstrations. The expectation step, with initial guesses for the parameters of our mixture model, partial membership of each data point in each constituent distribution is computed by calculating expectation values for the membership variables of each data point. That is, for each data point xj in distribution Y, the membership value Y, j is. The maximization step, with expectation values in hand for group membership, Plug-in estimates are recomputed for the distribution parameters. The mixing coefficients I are the means of the membership values over the n data points. The component model parameters I are also calculated by expectation maximization using data points xj that have been weighted using the membership values. For example, if I is a mean I1/4. With new estimates for I and the IIs, the expectation step is repeated to recompute new membership values. The entire procedure is repeated until model parameters converge. Markov chain Monte Carlo equals. As an alternative to the M algorithm, the mixture model parameters can be deduced using posterior sampling as indicated by Bayes' theorem. This is still regarded as an incomplete data problem whereby membership of data points is the missing data. A two-step iterative procedure known as Gibb sampling can be used. The previous example of a mixture of two Gaussian distributions can demonstrate how the method works. As before, initial guesses of the parameters for the mixture model are made. Instead of computing partial memberships for each elemental distribution, a membership value for each data point is drawn from a Bernoulli distribution. The Bernoulli parameter I is determined for each data point on the basis of one of the constituent distributions. Draws from the distribution generate membership associations for each data point. Plug-in estimators can then be used as in the M step of M to generate a new set of mixture model parameters, and the binomial draw step repeated. Moment matching equals. The method of moment matching is one of the oldest techniques for determining the mixture parameters dating back to Carl Pearson unregistered trademark S seminal work of 1894. In this approach the parameters of the mixture are determined such that the composite distribution has moments matching some given value. In many instances extraction of solutions to the moment equations may present non-trivial algebraic or computational problems. Moreover, numerical analysis by Day has indicated that such methods may be inefficient compared to M. Nonetheless, there has been renewed interest in this method, for example, Craigmile and Titterington and Wang. McWilliam and Lowe consider the characterization of a hypercuboid normal mixture copular in large-dimensional systems for which M would be computationally prohibitive. Here a pattern analysis routine is used to generate multivariate tail dependencies consistent with a set of univariate and bivariate moments. The performance of this method is then evaluated using equity log return data with Kolmogorov Eurospan of test statistics suggesting a good descriptive fit. Spectral method equals. Some problems in mixture model estimation can be solved using spectral methods. In particular, it becomes useful if data points I are points in high-dimensional real space, and the hidden distributions are known to be log concave. Spectral methods of learning mixture models are based on the use of singular value decomposition of a matrix which contains data points. The idea is to consider the top k singular vectors, where k is the number of distributions to be learned. The projection of each data point to a linear subspace spanned by those vectors groups points originating from the same distribution very close together, while points from different distributions stay far apart. One distinctive feature of the spectral method is that it allows us to prove that if distributions satisfy certain separation condition, then the estimated mixture will be very close to the true one with high probability. Graphical methods equals. Tarter and Locke describe a graphical approach to mixture identification in which a kernel function is applied to an empirical frequency plot so to reduce intra-component variance. In this way one may more readily identify components having differing means. While this I method does not require prior knowledge of the number or functional form of the components, its success does rely on the choice of the kernel parameters which to some extent implicitly embeds assumptions about the component structure. Other methods equals. Some of them can even probably learn mixtures of heavy-tailed distributions including those with infinite variance. In this setting, M-based methods would not work, since the expectation step would diverge due to presence of outliers. A simulation equals. To simulate a sample of size n that is from a mixture of distributions phi, I equals 1 to n, with probabilities pi. Generate n random numbers from a categorical distribution of size n and probabilities pi for I equals 1 equals to n. These tell you which of the phi each of the n values will come from. denote by me the quantity of random numbers assigned to the ith category. For each I, generate me random numbers from the phi distribution. Extensions: in a Bayesian setting, additional levels can be added to the graphical model defining the mixture model. For example, in the common latent Dirichlet allocation topic model, the observations are sets of words drawn from D different documents, and the K-mixture components represent topics that are shared across documents. Each document has a different set of mixture weights, which specify the topics prevalent in the document. All sets of mixture weights share common hyperparameters. A very common extension is to connect the latent variables defining the mixture component identities into a Markov chain, instead of assuming that they are independent identically distributed random variables. The resulting model is termed a hidden Markov model and is one of the most common sequential hierarchical models. Numerous extensions of hidden Markov models have been developed. See the resulting article for more information. History, mixture distributions and the problem of mixture decomposition, that is the identification of its constituent components and the parameters thereof, has been cited in the literature as far back as 1846, although common reference is made to the work of Carl Pearson as the first author to explicitly address the decomposition problem in characterizing non-normal attributes of forehead-to-body length ratios in female shore crab populations. The motivation for this work was provided by the zoologist Walter Frank Raphael Weldon, who had speculated in 1893 that asymmetry in the histogram of these ratios could signal evolutionary divergence. Pearson's unregistered trademark S approach was to fit a univariate mixture of two normals to the data by choosing the 5 parameters of the mixture such that the empirical moments matched that of the model. While his work was successful in identifying two potentially distinct subpopulations and in demonstrating the flexibility of mixtures as a moment matching tool, the formulation required the solution of a 9th-degree polynomial, which at the time posed a significant computational challenge. Subsequent works focused on addressing these problems, but it was not until the advent of the modern computer and the popularization of maximum likelihood parameterization techniques that research really took off. Since that time there has been a vast body of research on the subject spanning areas such as fisheries research, agriculture, botany, economics, medicine, genetics, psychology, paleontology, electrophoresis, finance, sedimentology, geology and zoology. See also mixture density, mixture, flexible mixture model. Hierarchical models graphical model, hierarchical Bayes model. Outlier detection Ramsuk. References. Further reading. Books on mixture models Overath, B.S. Hand, D.J. Finite mixture distributions. Chapman and Hall. ISBN 0-412-22420-8. Lindsay, B.G. Mixture Models, Theory, Geometry, and Applications. NSF-CBMS Regional Conference Series in Probability and Statistics 5. Hayward, Institute of Mathematical Statistics. Marin, J.M. Mengerson, K. Robert, C.P. Bayesian Modeling and Inference on Mixtures of Distributions. Day, D. Rao, C. Are Essential Bayesian Models. Handbook of Statistics, Bayesian Thinking, Modeling and Computation 25. Elsevier. ISBN 9780444537324. McLaughlin, G.J. Peel, D-Finite Mixture Models. Wiley. ISBN 0-471-00626-2. Press, W.H. Tucholsky, S.A. Vettling, W.T. Flannery, B.P. Section 16.1. Gaussian Mixture Models and K-Means Clustering. Numerical Recipes, The Art of Scientific Computing. New York, Cambridge University Press. ISBN 978-0-521-88068-8. Titterington, D. Smith, A. Makov, Use statistical analysis of finite mixture distributions. Wiley. ISBN 0-471-90763-4. Application of Gaussian mixture models equals, Reynolds, D.A. Rose, R.C. Robust text-independent speaker identification using Gaussian mixture speaker models. IEEE Transactions on Speech and Audio Processing 3, 72 €83 doi, 10.1109/89.365379. Permuter, H. Francos, J. German, I.H. Gaussian mixture models of texture and color for image database retrieval. IEEE International Conference on Acoustics, Speech, and Signal Processing, 2003. Proceedings. The journal version, Lemke, Wolfgang. Term Structure Modeling and Estimation in a State Space Framework. Springer Verlag. ISBN 978-3-540-28342-3. Briego, Damiano. Mercurio, Fabio. Displaced and mixture diffusions for analytically tractable SMILE models. Mathematical Finance Eurobaclia Congress 2000. Proceedings. Springer Verlag. Briego, Damiano. Mercurio, Fabio. Log Normal Mixture Dynamics and Calibration to Market Volatility SMILES. International Journal of Theoretical and Applied Finance 5, 427 doi, 10.1142 per second 0219024902001511. Alexander, Carol. Normal Mixture Diffusion with Uncertain Volatility, Modeling Short and Long-Term SMILE Effects. Journal of Banking and Finance 28, 2957 €80 doi, 10.1016/J Bankfin. 2003.10.017. Stiliano, Yanis. Pantazias, Yanis. Calderero, Felipe. Leroy, Pedro. Severin, François. Skimk, Sasha. Bonal, Rolando. Matter, Federico. Valsamarkis, Athanasios. GMM-based multimodal biometric verification. External links, Nielsen, Frank. $K$MLE, a fast algorithm for learning statistical mixture models. ARZiv, 1203.5181. The SOC are demonstrations of M and mixture modeling page applied to finite mixture models, maintained by DL-DAO. PyMixer EuroPython mixture package, algorithms and data structures for a broad variety of mixture model-based data mining applications in Python. Scikit-learn mixture GMM EuroPython package for learning Gaussian mixture models, previously packaged with SciPy and now packaged as a scikit. GMM MATLAB code for GMM implementation, GPU-MIX C++ implementation of Bayesian mixture models using M and MCMC with 100x speed acceleration using GPU. 2. MATLAB code for GMM implementation using M algorithm. 3. JMEF, a Java open-source library for learning and processing mixtures of exponential families. Includes a MATLAB wrapper. Very fast and clean C implementation of the expectation maximization algorithm for estimating Gaussian mixture models. McClusters in a package for mixture modeling.